Hey everybody, this is Larry. This is day 27 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's farm. Just a quick update for those of you who followed me the last couple of days. I got off jury duty, so yay, I am free. I'm a little bit tired today. Still took the whole day. It's like 9 to 5. I got a little bit early. I haven't had a 9 to 5 day in so long that it's just like I don't know. Even when I had a job, I did not wake up at like 8 a.m. or whatever it is. So it's been kind of rough, and I just have not been sleeping enough, which makes the running and everything kind of suboptimal. So yeah, but I think I'm still working out some kinks on the new channel. I do want to kind of just, you know, in case you're a little bit interested but not too interested yet. So it's still a little bit of building out that mystery, suspense, if you will. But it's just just a channel of things I find interesting, but also hopefully in a way that, well, one is that you find interesting, but just nothing too intense, just about how to get yourself to keep going. And right, I think the hardest thing about these things is that it just operates on a different time scale, and what I mean by that is just that it takes a long time to really get good at it. um of course good is debatable, and of course everyone has different goals, but I'm just saying, like, and maybe hopefully I can kind of just summarize things that I read way too much, and just kind of give you a little bit of a push to keep on going when you need that energy sometimes. And I know I do sometimes I'm just like, wow, I don't know. And today, for example, I did it's supposed to be a minor update, and I keep on rambling, but yeah, I just kept on, because I'm trying to keep so one of my goals, because I have many. The hard part of what I'm doing, like physically, with respect to my exercising and workout routine, is that I'm doing like a couple of things at the same time, right? Because and I want to, like, one of my goals, and I don't know if I'm gonna hit this because I have to fix some nagging injuries, but like one of my goals is to get up to 405 on this, or what is that, 160 kilos or something? I do 160 or 180, I forget because I don't have a calculator. 405 pounds, 2 kilos, 185 or 183 kilos, right? So 180, say, because I think maybe Americans round up, I don't know. But yeah, 180 kilos on a squat by the end of the year. But I don't. Initially, I thought I could probably have a good chance, but I think I'm working out some injuries because I don't want to hit it and then just be like injured, and then I'll just be like, well, you hit an arbitrary number, but at what cost? I want to do it, in a safe way, in a deliberate way, and just and that's how I always think about. Well, not always, because when I was younger, and most of the people who are watching this is probably younger than me now. When I was younger, I just want to get everywhere as soon as possible and as fast as possible, whatever it takes, right? Um, but life really rarely works that way. Sometimes you spot people who go really quickly to get to where you want to go very quickly, and there's a bit of element of luck, the right place, right time, right preparation, everything, right? But everything else just takes a while. Um, yeah, so we'll see what happens. And yeah, I'm trying to do that 4-5 squat or 180 kilo squat, but I'm also trying to at the same time, starting from mostly nothing, because I didn't used to do well. I think I did cardio when I was much younger, but I haven't done it in the last decade just because of, well, COVID and just working really hard and stuff like that. Just never had time for it, was my excuse anyway. So I'm trying to also get to like an 8-minute pace for as long as I can. I don't have an year-end goal yet, but my next goal is just 8-minute pace at 5K, and then maybe 8-minute pace at 10K, and then dot. So, like, it'll be more of a progressive thing, right? So yeah, so I'm trying to do both of them at the same time, and try to yeah, and that's been way tiring, way draining. Um, but why I brought that up is that because I think that it kind of relates to me in some way, is that um, in a way you're fighting against everything that your body and your mind wants to tell you, just to stop. Because it's so comfortable, so easy to stop. Every minute, every second, when I'm like, and today I did like long intervals, which means that I'm trying to go at a pace that I was trying to go as fast as, so I was trying to do like a 7-minute pace, which for me is fast because I'm just not in shape for it, for as long as I can. And definitely, and today I did like, I did pre-mits of 5, 4, 3, 2, 1, which is, 5 minutes, 4 minutes, 3 minutes, 2 minutes, and 1 minute, and with a minute intervals and recovery in between. And at the end of every of those intervals, I'm like, yeah, you just want to give up because it's so easy to give up. You don't have to do anything to give up, and then you can have all your breathing back, and you have everything. Everything is so easy, but you just gotta tell yourself, and in a way, maybe a little bit of self-delusion, if you will. The way that I do it is just that, I'm like, oh, you could give up. Just give up after another 20 seconds. And then 20 seconds later, all right, come on, Larry, you didn't come this far to, give up now. Just give me another 20 seconds. And then basically this entire way for 5 minutes, right? So, yeah, and generally, these are pretty hard for me because if it's not hard, I would not do it that way. Meaning that if 7 minutes was easy for me, I would have done it at like faster, right? So these are always hard. Anyway, did not really expect this rant to go on for 6 minutes. My apologies. Hopefully, you're still watching or something. But hopefully this is just an insight, right? Everything you want and everything that you strive for is a little bit hard. Because if things are not hard, then you have to ask yourself, why are you doing it? Right? Why are you wasting your time if it's not hard? Right? Like if you're easy, then you're just like, what are you doing with your is easy? Okay, look, some stuff is practice and some stuff is, there are deliberate goals for different things. Like I may solve a easy problem just because, I have to maybe learn some APIs or practice this deliberate thing, or maybe just practice my typing, right? So there are goals and different things. But if you're going to do hard things, make sure they're hard, right? Don't fool yourself, or it's not in that way. That said, like an exercise, like in Leetcode, you can't really just force everything very quickly. I mean, if you did, you probably just had the background, right? And what I mean by that is that, let yourself rest, let yourself recover, let yourself learn. This is how, even in learning, there's this idea of spaced repetition, right? Like, and this is just memory-based things and not necessarily Leetcode, because for Leetcode, I want you to kind of actually learn to problem solve and not just learn to memorize, right? But like, this idea of spaced repetition is that, it takes, if you do the same thing K days and then and then shorter intervals as you kind of go along, then you just, or maybe longer, I forget, yeah, long intervals that you go, but then that's when you actually begin to learn things. And that's where the recovery, when, get enough sleep, eating right, all these things all fits together with, Leetcode, workouts, everything, right? You probably most of your learning is probably done when you're sleeping and you're recovering, and just like, and you have to eat well to feed your brain and all these things, right? And listen, when you're young, you get away with it, and I was young, I got away with it, but now, I'm paying for some of those costs, like everything hurts a little bit, but all right. That was meant to be like a minute rant, and I don't know, sorry friends, but also I mean, this was everything unscripted, because it was scripted. This is kind of, I don't know, but these are the kind of things that maybe in a way it's a preview for my channel, my other non-programming but still tech related motivational channel. It's just this idea, right, of, I don't know, different ways to look at things, different ways to kind of keep going, and different ways to push yourself, hopefully, and different people respond to different things. So, all right, let's actually start. My apologies, 9 minutes into the thing, but hopefully, you actually enjoyed that. And if not, then I don't know, then don't subscribe to that channel. Send it to someone you hate, and maybe they'll waste time on my channel. I don't know. But all right, let's actually get started. 713 subarray product less than k. Given an array of integers nums and an integer k, return the number of contiguous subarrays where the product of all the elements in a subarray is strictly less than k. All right, product, right? Okay. Mm, I mean, this is going to be sliding windows. This is kind of a way um, yeah. I mean, let me step back for a second. Right? I mean, I think sliding window, because I have this different idea of sliding windows. I think sliding windows, for a long time I thought about this thing about greedy and extending and stuff, and I've been teaching it that way for a long time. As you know, if you've been watching me doing sliding window problem, well, or whatever, or just problems with sliding windows. But I think now that I'm thinking about it a little bit more, and kind of working into other problems that are not sliding windows, and they're just like, this idea, right? They're like, because I think there's a more, I guess what I want to say is that there's a more general way to solve this, where sliding window is one of the sub problems of you. Sub problems, it's kind of a little bit, it's just like a sub, in a subcategory, if you will, of thinking about it in the hierarchy of how I think about this, right? And what I mean to say about that is that, and sometimes you hear me talk about this a lot, and maybe for a while in the past, I'm just creating this example that's longer, just to kind of whatever, right? And maybe I'll just spell on the keyboard, it doesn't matter. Maybe in the past you've heard me for some certain problems talking about contributions, right? And what I mean by contributions, usually when I say it, and I don't know, I think I made up this term this week. I mean, I didn't make up this term per se, because I think it's a mathematical thing about, contribution to the sum, etc. But I think, like, in terms of it being like a thought process, a way of thinking, maybe you could even call it a category of problems, if you will, or maybe a category of solutions or techniques anyway, maybe not problems. Is that, okay, what I mean by this is that we can go for each one, right, and figure out what is the contribution to the final answer in some way, right? And you go from left to right, with a for loop. And here, that's where the sliding window is kind of come into play, is that it allows us to calculate this contribution in a more effective way, right? And in a more effective in terms of complexity and so forth, right? And what I mean by that is that this contribution is, okay, let's say we're at the number 6, right? How many subarrays, like I mean, obviously it depends on the problem. Usually it deals with subarrays, because I guess maybe not always, but depending on the problem. But very often, at least if it deals with subarrays, it's often either sliding window or some kind of stack-based greedy solution sometimes, at least for problems on the easier level anyway. But yeah, what I want to say is that, okay, given this element is the last element in the subarray, how much does it contribute to the final answer, right? And basically you just ask that for every element. And here, this is where sliding windows kind of come in, but I'm going to think about it backwards yet. So no sliding windows yet, but you could say, okay, well, if 6 is the last element, then can 2 be a first element? Yeah, because, okay, I forgot to mention k. Let's just say k is equal to 100, right? Can 2 be the first element? The answer is yes, because 6 times 2 is 12. Can 5 be the first element? Well, yes, because 12 times 5 is 60, right? So yeah, and then next is no, because, well, now you're at 600. But yeah, but then now you know that 5 could be the first element. I'll put F for first. That means that now you have, and this is where I always talk about degree of freedom. And when I say degree of freedom, I just mean the number of things you can choose, right? And here I mean that, okay, you have three degrees of freedom, right? Or the other three, because you could choose 5 to be the first element, you could choose 2 to be the first element, and you could choose 6 to be the first element, right? So 3 contributions to the answer is the 6, right? So then here you could say maybe the answer is 3, and then maybe, I don't know what the other ones are. I guess the answer for this one's also 3. But okay, it doesn't matter, right? It's just, you sum up all the contributions and then you get the answer. So that's how I think about these things now with contribution. And then now, speaking, with all that in mind, right? Now you can think about things with respect to the sliding window, right? Because now the idea here is that, okay, let's say we're at 6. This is the current this element, and f is the first element, right? And then now we slide the 6 to the 10. Then what happens? Well, we know that, and then now we could calculate in a cheap way, which you know how. I mean, I'm kind of hand wavy some of the mechanics, because I want to generalize it a little bit for similar problems and not this problem. But yeah, going from 6 to the 10, it changes the in this case the product, right, by multiplying by 10. Pretty straightforward, right? Pretty obvious. But then now, because when you multiply by 10, this becomes 600 or something, right? And 600 obviously is too big. So then now you quote unquote slide your window to try this one. It's 2 being the first element good, right? And so forth. So this is now just actually 2 is still not good, right? Because it's 120. But so then you slide again to 6 and 10, and then you go, okay, 10. Now this is good. So then now the contribution is 2, right? Okay. So that's basically another way of thinking about sliding windows that I've been kind of playing around with in the last couple of weeks, most on contribution problems. But now that I'm thinking about sliding window problems as contribution problems, maybe you can think of it that way as well, right? Yeah, and that's pretty much the idea, right? Because then now, of course, the invariant, a core part of sliding windows in general is loop invariance and stuff like that. And some of the invariant is just that, you can be able to divide things out cheaply and multiply things in, and kind of basically maintaining the stuff inside, quote unquote, inside the span or the subarray or the set or whatever you want to call it, in a quick, cheap way, right? And in this case, it's going to be O of 1, roughly speaking, not assuming constant time integer multiplication, division, if you really want to be pedantic. But you can also imagine that, maybe in another thing you have to, keep track of frequency of stuff, which is also another common problem that we've seen for sliding windows, right? Or maybe even another thing of like, maybe you have to do some like getting the max element. So then here you have a heap or something like this, or maybe not a heap because of you could do a lazy heap, but like a heap like object, right, or something like that, and there'll be log n, but that's fine because that you only have n elements, right? So there definitely a lot of different ways to think about it now that you are able to kind of think about this problem in terms of contribution problems, right? So yeah. Okay. So now, yeah, so let's do it. So then now we can just solve it, right? I think we already mostly talk about most of the ideas. We can just go, I think. Yeah, I always like to write this in. I don't even know if it's necessary per se, but ooh. And you can, I always keep these things as like left right, but you can always use your own notation, right? And the idea here, and for debugging purposes, you want to be as precise as possible. And here we want an open end, I'm forgetting the interval, right? Open interval. And what I mean is that left is exclusive. So that means that it does not include left of. Is that true? No. Left is inclusive. Yeah, and right is inclusive as well. Well, not yet, but yeah. Is that true? Yeah, I guess the way that I write it is fine, right? yeah, and then maybe we'll just have the current product is equal to 1, just as a, identity for product, right? And then here, the idea is that, okay, technically, I guess right is not inclusive on the top, but we just want to kind of keep track of how we want to express these things. And then here now, product, num sub right, and then now right is inclusive, right? So then now, the product includes right and left, if you think about it, right? So left, right is inclusive because at this point in the code execution, yeah. But then now we want to get rid of, well, we still want it to be true, but then now we go, well, product is greater than K, and left is less than or equal to right, then product we divide it by num sub left, right? And then left increment by 1. And then of course in this case left can be greater than right because this is how, because they're both inclusive, that's fine. So this is still true afterwards, but then now the invariant is also that product is now less than or equal to K, or left is greater than right. So in theory the product is going to be 1, but it's just like a placeholder 1, because you have like a no element no set thing, right? So you're taking a product of no elements, no elements, right? So then if this is the case, yeah. But also, oh yeah, we need a count thing, right? Number of contiguous subarray, right? So we have total is equal to 0. And then now you can maybe say total, we can add right minus left plus 1. It turns out that if left is, if this has 0 elements, this also works. But if you really want to, you could just write something like this, just in case you didn't want to think about it or proof it, which I often do, so that, if this is negative for whatever reason, you just get 0. But yeah, but basically this is to kind of give us the degree of freedom, right? And this is just that, and you can kind of play around with small numbers to prove yourself that this is correct. That's what I do anyway. Like in case you're wondering about off by 1. But for example, with right is equal to left, that means that you have 1 element because it's inclusive, and then this gives you 0, this gives 0, plus 1 is 1, and then you can play around small numbers. And then that's pretty much it, really. I think, unless I'm missing something, which I guess I do miss a lot. Oops. I didn't know that I could run code too quickly because, it has to be strictly less than. Okay. So then, yeah, okay, fine. So strictly less than just means that now, well, we set this actually, right? So if we kind of make this small change, then now we can make this small change, and this should give us the right answer, right? Very simple. And this is where, I mean, you shouldn't over comment code because, as my mentor used to say, that's just an excuse for bad code. But I'm kind of just writing it here so that you can kind of see what the invariants of, so then you can trace it through. But yeah, overall, this is a good, I think a lot of people learn some variation of this sliding window very early on. So I want to give a little bit of a different spin, a little bit of a different thinking about it. I mean, the code, to be honest, is still going to be, it's still mostly the same as how you would do it, even without this idea. But I think thinking about it in this idea of contributions will allow you to kind of extend this to other problems, the harder problems, more importantly, right? More difficult problems that takes that as the idea, but without the sliding windows, right? So yeah, cool. What is the complexity here, right? This is linear time. I mean, I think some people also have questions about amortized analysis, but the thing is that left, because left is always less than or equal to right, this loop inside means that left can only increment the number of times you go to right. So that means that this loop will execute at most O of n times in total. So this is O of n times plus O of n. So this is going to be O of n in total. This of course assumes that, like I said, multiplication and division is constant, which in this case it should be because k is less than 10 to the 6, and because of that, then you're bounded and it's a constant integer division, multiplication and division, and each item is also only up to 1,000. So if you want to prove some other bounds, because you're using another language, for example, where you have 32-bit ints, that's something you can do as well. But okay, that's all I have for this one though. I'm gonna do an extra bonus poem after this. Let me know what you think. Stay good, stay healthy, to good mental health. I'll see y'all later. Oh man, I'll see you later and take care. Bye bye.